Good evening and welcome to the APAC edition of the vBrownbag podcast. I'm Alistair Cook and it is May already. I cannot believe it's May. Starting a new series this week, and very pleased to have with me the famous virtual Irfan on Twitter. We're starting looking at some performance things, and Irfan, welcome and thanks for joining me, and particularly thanks for proposing this series. It's really good to have somebody suggesting we should cover some things.
Yeah, thank you so much. I am really excited to join you guys and kick off, I think, what's going to be a very interesting series, and I'm trying to kind of do a unique perspective with looking at performance of virtualized environments. I think that people look at it from different perspectives. Spent a lot of time at VMware. I don't know if your viewers are aware, but I had the honor and privilege of being part of the early days of the virtualization revolution, joined VMware in 2002, and worked kind of deep in the bowels of the virtual machine monitor and the VM kernel from fairly early on, and ended up working on distributed systems like storage DRS and storage IO control. So, everybody has a different perspective for how to look at performance, and having spent many years in the VMware's performance team, also in the early days, the first 4 or 5 employees in that team, ended up with a unique perspective of kind of where the typical problems are and how to kind of look at them in a different way than I think a lot of people kind of by default start to look at them.
I wanted to put some context on that 2002 start date, because I was thinking about my time with working with VMware products, and my recollection is 2002 would have been about VMware Workstation version 3 and just at the genesis of the VMware GSX product, and probably was ESX a product at the time?
Yeah, ESX was just very nascent at that time. Nobody really was using it. People were trying it out, but nobody was really, even putting
it had a 1 in its version number, didn't it?
It did. It did. And Workstation 4, my first project was to help get Workstation 4 out the door. And I worked on Workstation 4, then Workstation 5 and GSX in the early few months of my time there, and then switched over to focusing exclusively on ESX, which basically continued for the next 7 or so years. Yeah, so This is 2002 is very early days. The company was about 200, maybe a little less than 250 at the max at that time. And like I said, being there 9 years, I ended up leaving when the company was more than 13,000. So that was a nice, interesting kind of journey of scale and growth and challenges and so forth. So, it was a nice journey.
Yeah, and I, of course, first had real contact with you through the first set of vBrownbag Tech Talks at VMworld. And by the way, if there's any sponsors listening, do get in touch, because we are going to be returning for the 3rd year of Tech Talks at VMworld this year. And if any of our guests, any of our listeners are going to be at OpenStack Summit next week in Atlanta, the vBrownbag crew are absolutely delighted to be doing Tech Talks at the OpenStack Summit. So come by room B207 and you'll find us hanging out there. But yes, I came across Irfan when CloudPhysics was making quite a lot of noise as being this new, really well-liked sort of, that the whole community loved CloudPhysics, because you guys gave something away for free, which, as the enthusiast, is our favorite price to buy things for. And so, yeah, you present a little bit about it, and particularly showed some of the things that the community were generating around CloudPhysics too.
Yeah, it's actually really exciting. And by the way, the product, it still has a free tier, and this is the kind of the free forever tier. We call it the community edition of the product. And our commitment is that, when community members use their own effort and use our tools to create analytics for their own purpose, but then selflessly share them for other community members, that functionality should be free for all community members. So it's no different than Alan Renew, for any one of the famous bloggers that you and I know and love that are doing PowerCLI or Perl or any other type of kind of community service scripting that, given that it's open public APIs and we're sharing with each other, there's no price tag on it.
Yeah, so it's that community-generated and shared content continues to be available to the rest of the community, and it's I think a very astute business model to be recognizing that can actually be really helpful to your business. As I wrote about on my blog after Irfan and I last met at the Virtualization Field Day 3 in February, it would have been, wasn't it? February, March? Some months ago in San Francisco, and that was one of the perspectives I kind of got out of it was just how smart a model this let people create something and then keep it free, yet it's hugely valuable to you.
Yeah, and by the way, the other thing that we did, which people really gave us great feedback on, was to keep a free trial of the enterprise product, which is allows people over the first couple of weeks. I think currently actually the free trial is even 30 days.
It is 30 days?
Yeah, it's still 30 days right now, and gives you the power of the full product to try out in your environment.
Yeah, and it's not like it's a product that takes 3 weeks to learn what's going on in your environment and just starts to deliver value as you're getting shut out of it. Within the first 24 hours, there's value out of that free trial, which I think is really cool.
Yeah. So the setup is about 5 minutes, and then after the setup, almost all of the functionality is instantly available. And kind of my challenge to my engineering teams always is that by the time that the customer has switched over from their vCenter client where they used their OVF tools to automatically install this virtual appliance, and by the time they switch back to the browser that they use to download that virtual appliance, that we should be starting to deliver value. That's within a minute or so. And so that's the challenge that we have internally, and I think we've come pretty close already, and we continue to improve that. So a lot of the analysis and a lot of the capabilities of the system are immediately available, and of course, like you said, from the performance data and some of the trending and so forth starts to kick in within the first day, and a lot of other functionality starts to really, really advanced kind of performance time series functionality starts to kick in as more data arrives.
Yeah, so as you know, and those have been following for a while, the CloudPhysics product is very, very well liked, and but we didn't come here just to be a straight love fest for CloudPhysics and attract you some more customers. We were also going to help people to solve their problems through the sequences, as is our want on vBrownbag.
Yes. So in fact, my goal is to make everything we talk about extremely generic. In fact, today I don't think I really have more mentions of CloudPhysics than even just literally this slide. I think these are the only slide that has a logo even, because there's just like CloudPhysics has a lot of free tools, there are other free tools, and that can get us pretty far. The key thing is us really understanding how to use them and what the concepts are behind this. And so in this series dealing with performance, I'm going to start off really focusing on storage workloads and spend a session or two really delving deeper into that and understanding how we can tell what we're actually running is one of the great ironies. And that's why the title of this slide here on this deck is a little provocative, right? What's your shape? The workloads that you're dealing with, if you don't understand their shape, it's very hard to make much sense of the performance data and the performance troubleshooting workloads that you really need to be engaged in. So this is not a vendor pitch at all, and I hope that as we go through that, we can keep it interactive and you can help me kind of guide the conversation in the right direction.
So everybody who's in the live with us, do ask questions, do put things up in the chat as we go. I'll be keeping an eye on those, and hopefully we'll have a good interactive session. And we've got a few people on the line, so particularly some familiar faces, some good friends out there. The other thing I wanted to say is I'm really pleased that we're focusing on storage at the beginnings here, because my personal experience is that storage is often the silent killer, that people are having a performance problem with their virtual machines, with the applications inside them, and yet all of the superficial performance metrics look fabulous. There's no shortage of CPU and memory, and all of the networks look good, but people often find that the thing that's causing them pain is actually the storage underneath, and so I'm glad we're starting with storage as a performance dimension to look at.
Yeah, for what it's worth, the VMware internal statistics around performance problems that were raised to tech support and raised up to the performance team. So that means this is kind of a very important customer, and the problem is pretty severe. 9 times out of 10, the problem would be traced back down to something to do with storage. 9 times out of 10. So completely agree. The empirical data matches what you have seen. I think what most of us have seen. So.
Yeah, and I think that was Scott Drummond's kind of thing when he was with the performance management team was it was always storage, and it was always misunderstood storage.
Yeah, that's right. That's right. And hopefully he's watching, because he's over in APAC these days.
Yeah, he's up in our part of the world.
In Hong Kong.
Yeah.
So just to kind of set a little bit of context for our viewers, the virtualization journey has been just phenomenal, and all of us together, those of us who've been in the virtualization industry, either on the vendor side or on the administration and architecture side in the field, we've all kind of helped this thing happen. So I think we should always be proud of the accomplishment, the joint accomplishment of the industry in this meteoric rise of virtualization in the data center. And if you kind of look out, it's not slowing down or stopping. Out to 2014, the IDC survey suggests that we're going to have about 100 million virtualized workloads in the world, which is just absolutely phenomenal. For comparison, if you look at, for instance, the size of Google's data center, right? So we don't have real data on this because Google considers it a trade secret and they don't share it. In fact, one of my co-founders at CloudPhysics is from Google, and he doesn't even tell me. But they've got a small number of millions of machines that they're running, and and then the scale of commercial computing is 100x that kind of thing. So that's where the trends are going, but in reality, as customers have started to adopt virtualization and kind of the private cloud, paradigms, that the promise hasn't always kept up, and this has kind of always been very interesting. When I was at VMware, we were always intrigued by why people would kind of slow down at 50% virtualizing their enterprise, and you slowly realize that the ROI of doing consolidation from virtualization is actually pretty dramatic in the earliest days of consolidation. It's remarkable, this is the stuff that promotions are made of.
So this is when you're virtualizing the sort of general lightweight infrastructure, the easy stuff.
Yeah, exactly. And your consolidation ratio is not really that high yet, right? So you're getting the immediate CapEx and the OpEx savings of having to not worry about physical machines, and being able to live migrate and to do vMotions and getting better uptimes because you can do host maintenance modes and things like that, right? So yeah, no doubt about that. But as customers kind of go past that early virtualization time and want to increase the consolidation to get even more CapEx savings, because they find that even after virtualization, their CPU utilization and disk utilization is not very high, and they think that hard consolidations are possible. But that's really where the pain kicks in. We saw this over and over again at VMware, and really it's the new operational hazard and new operational challenges that result from packing more workloads. And now performance problems arise, and it was not uncommon to see performance problems that would get raised that would take a week or 2 or a month to get resolved, and all of a sudden you're in a situation as a customer where your smartest people, your sysadmins, dealing with virtualization, kind of the best of the best, are just mired in these problems that take too long to figure out, and because the tools are not there, and because there's very little predictability yeah, it results in a tremendous amount of risk. So some people look at this and call it the Viagra slide, but the point is that unless we up our mojo, these sets of issues are just going to continue to come back and bite us. So that's kind of I'd say the highest level context here, some of the things that I wanted to talk about in this series. We'll see if we can get to all of these, but challenges, will performance suffer if I consolidate more? That's kind of obvious from the previous slide. How do I ensure that we can meet our SLAs? This is how do I measure it? And you were talking, Alistair, about how all the dashboards for storage are honky-dory, and yet there's a problem, and you dig deep enough and you realize it was storage all along, and your tools were just not showing it. And so the big part of that is how do I measure reliably my SLAs, and then what steps do I take to make sure I can achieve them? Really important question these days is, will I really benefit from SSD caches, right? A lot of our friends are working for some sort of an SSD acceleration company or another these days. There's dozens of them. So how do I plan for that? How do I plan budget for that? How do I plan, how much I need? How do I size my environment, and so on and so forth? So hopefully we'll start to kind of dig into these as we go along in this series.
And kind of help out with the customers who are heading through that. We've done the easy stuff. We're heading into the harder stuff, the really critical or more critical and high visibility applications. Which my particular part of the world, we've been virtualizing for a while, and we've seen many of these pains. But I know other parts of the world are much slower to the uptake. And I was in Southeast Asia recently, and I can tell why Scott's over there, because there's some interesting challenges in that part of the world, and people are actually addressing and kind of hitting these things, and they want to go straight from no virtualization to everything virtualized without learning how to handle these challenges and how to move through the different pieces. So it's an interesting kind of context.
Yeah, I agree with that. So ultimately,
one comment from the floor. Even Dell is getting into the caching components.
Yes, I heard about recently. Absolutely, and it's actually a pain point that people are feeling, performance problems, and we're tempted to just go ahead and resolve them buying hardware.
Big pile of money solves a lot of problems.
That's exactly right. You could throw hardware at this problem. Or you can do it more intelligently and maybe still throw hardware at the problem, but and the question is always like, okay, how much hardware should I throw at this problem? Right? And that's where you need to get a little bit more intelligent, and we'll definitely talk about that as we go. But at the highest level, Alistair, here's kind of where I'm still setting context here, but here's where kind of my interest is in where I want to see our industry go. I sit back and I ask these questions. Why is it that data centers cannot be designed the way that we do civil engineering? So whereas if you're going to build a bridge today, you're going to use CAD software, and before any concrete is poured, in fact, before any steel is even ordered, okay, you know how that bridge is going to behave under many different sets of circumstances. And you're going to do this typically in CAD software to design the infrastructure and model the costs and do multi-vendor analysis and all this sort of stuff. And you're going to be so good at it that if somebody comes up and says, how much load can this bridge take, you can go span by span, inch by inch, and say, this particular section of the bridge can do 2 tons per square meter or whatever.
Yeah, and if we certify out trucks to take another 20 tons worth of workload, then these outer 2 lanes have to be no trucks. Only the center lanes should allow trucks with absolute certainty that this is the safe place to run the trucks.
Exactly. And so that's how we do civil engineering. If you're operating in airlines today, the logistics are really, really complicated. In fact, if you're running an airport, it's even more so, right? And nobody's sitting there back of the envelope and whiteboarding the basic solutions here. We're using, logistics techniques and operations research techniques to maximize. The funny thing about airports is that they have to predict how much toilet paper to buy, and to have it ready depending upon how much traffic there's going to be. And Disney, for instance, I'm not sure how many of folks in APAC have been to a Disney resort, but it's a very large set of resorts in the United States. I'm not sure, maybe they're expanded around the world, I'm not sure. Very, very famous after Walt Disney and his kind of vision for entertainment and kids entertainment. And typically you can get tens of thousands of people showing up to any given day, if not a lot more, on busy days. And so the number of employees that Disney has to call in to service the demand from tourists and customers coming into their theme parks can differ by thousands on any given day, and they have to be able to predict this, otherwise they can't service the crowd. So that's how you operate on airlines or a theme park today. And the question always in my mind is, other large-scale operations systems have remarkably powerful tools to design and manage in a predictable way to really get ahead of problems as much as possible. But in our domain in this one, we don't have that. So the result of this can be actually pretty weird stuff and pretty, disastrous results in projects, and sometimes whimsical stuff. So I'm going to give you one example here, just as a cautionary tale. I was called in after the fact for a particular project that I'm going to talk about here. So I got to see kind of all the problems that happened in this project at a company that wasn't even our customer at that point in time. We were called in to help and learned a lot from. So a little bit about the company. It's a light vehicle automotive company established in the 50s, so a very traditional IT firm, very cautious folks, 4,000 employees and fairly large-scale, multi-billion-dollar revenues, publicly traded. And they had engaged in a caching project because they were getting a lot of performance problems that were not really getting solved. And so they said, okay, well, how about we try SSD caching? And a well-known and reputable vendor came in and helped them with that. And so they ordered a proof of concept to be done on premises and successfully completed, and decided to go in and do the investment to bring the equipment in, get it installed, and the production deployment of this was completed. But turns out, just within a few weeks, that the customer was very upset because they weren't seeing the benefits that they were supposed to see. And so then my team was called in, and we kind of started to do the forensics of this thing, and turns out that they had used fairly basic back-of-the-envelope, selection of virtual machines. And this is not even back-of-the-envelope, because that assumes at least a little bit of work. And what they had done was just said, look, here's the application servers, and here's kind of the in-memory type of database servers, which are very active, and kind of if you look at the profile of these things, they look extremely active, and so why don't we install there, because the performance problem seems to be there. And just so based on application identity, they went ahead and installed their SSDs that they had spent dear money to go and buy. But the project was a disaster because those VMs that were being accelerated, so-called, couldn't possibly benefit, and the whole thing was a tremendous waste. So we came in and we looked at those VMs. It turns out, like I mentioned, they were in-memory databases and application servers where there was not a lot of I/O that was actually even happening, and the type of I/O that was happening was not very cacheable. And so in this case, if the customer had done a little bit of homework and had access to better tools to select virtual machines that they would want to accelerate, they could avoid the whole thing. And in fact, in this environment, in that data center, there were plenty of VMs that were starving for acceleration. And that's really remarkable, and that without that knowledge, that the customer...
So with a straight kind of knee-jerk reaction of database servers need I/O, therefore we'll give them SSD and they'll be better, or at least SSD cache and they'll be better. but without any idea of working set sizes and the kind of behaviors of the applications. They use this valuable resource in the wrong place.
Yeah. So this is an extreme example, but I wanted to pick this example to say that, look, even for something like SSD caching, right, you have to be more careful. If you're not, you end up putting a lot of money into something that is not going to have a lot of results for you. And because the tooling oftentimes is not really good, you're not, if you want to get out of it, you're kind of back to square one. Okay, well, I have a lot of workloads on here on this SSD cache. Like, which ones do I keep on here, right? And how much do I give them? So, like you said, right, that's a key issue, especially with the expensive things like this. But the same sorts of techniques apply to more mundane problems, like a performance problem that occurs that you're trying to track down. So this is, performance of storage and how will my workload perform is kind of a question that I've been asked probably thousands of times over my career now. And the answer is always that it depends.
So you're a consultant now, it just depends.
But every time anybody would find out that I was at VMware and working on storage issues and performance issues, immediately people will say, well, here's kind of my workload, and why is it that it's not performing well, and what do you suggest, and what are best practices, and so forth. And the answer was always it depends, right? And so
it always is. The 2-minute conversation almost never gets you enough information to identify causes and resolutions.
Right. So after I heard about, after hearing this question hundreds of times, I actually just had to do something about it because I was tired of not being able to help customers and build some tools around it, which we'll start to discuss in a minute. But is the disk even a bottleneck? How do you determine if a VM is going to benefit from a change that you're thinking about doing? All of these things actually turns out they require detailed workload characterization. So you really need to be looking at outstanding IOs, and this is one of those metrics that I'm always amazed that more people don't use in their analysis. So this is outstanding IOs basically means the number of IOs that are queued to the disk from the virtual machine's point of view. So for instance, if you're running a very simple file copy workload, it's possible, let's say in Linux, it's possible that you're only issuing one virtual machine IO at a time. And then when that IO completes, you issue the next one. That one completes, you issue the next one. So that ends up being one outstanding IO. But if you're running...
And that'd be a classic copy this collection of files from one folder to another, where the underlying operating system is going to do one small file at a time and wait until that completes.
You're right, exactly. And then, and by the way, that if you're doing let's say the operating system is doing one file at a time, underneath the surface, deep in the bowels of the operating system, the IO subsystem of the guest is actually doing one input-output request at a time. So it could be, let's say, 64 kilobytes, or if the system is smart, it'll go to maybe 1 or 2 megabytes. So you read in a megabyte and you write it out. Then you read in another megabyte and you write that out. So that's why the only one IO is outstanding on the disk at a time. So if you were to measure it, you'd say, well, that workload has one outstanding IO. On the other hand, if you're running the database, it's going to have, say, 16, 20, 30 threads of little programs, little processes that are doing I/O. So in that case, it might be that the database has 30 read requests out at any given time, and maybe just as many writes if it's a write-heavy workload. So this is a very, very important thing. We'll get into that a lot more in a more detailed fashion in a minute. And then we have read-write ratios. And this is obviously pretty important. I won't go into it for all sorts of things, including just plain DRAM caching on your EMC or your NetApp or your favorite storage array, all the way to SSD analysis and so forth. Latency analysis, I mean, we'll see some extreme examples of how critical latency analysis is to really being able to solve your performance problems. And before you go off and make changes, really do an analysis of what type of latency you're actually seeing today, and don't just go by the basic stats that are often misleading, as you had mentioned in your introduction. And then finally, classic example that is really relevant these days is cache hit ratio. So this is a lot of gobbledygook that I've gone through, but I think when I tried in the slide deck to take a lot of time to introduce each of these slowly. And so there's a lot to take in right now, and it looks like it's a complicated set of things. But once you get used to it, you can do this sort of analysis fairly quickly using tools that you have at your fingertips, and get going. Of course, vendors like CloudPhysics have invested time to help you do some of that analysis more quickly, so you don't have to write scripts around it and so forth. But the point is that that's based on basic techniques that you can use today without buying any software.
Essentially, there's the underlying sort of physics background, actual physics degree background. So first principle stuff is here, and then there's layered on top of it things that'll apply that for you, which is always good.
Exactly. I mean, the techniques are I think fairly fundamental, and how far you want to take it is how far various tools want to take it. So pretty much everything I want to talk about, except the cache hit ratio analysis, can be done for free. And unfortunately, sometimes it's a little bit cumbersome. But when there's a serious problem, you don't worry about cumbersome. You don't worry about tedium. You need to just get it solved.
Yeah. And you also need to get to the very deep detail for when you do the post-incident review of exactly what went on and why.
Yeah, exactly. So, and from the higher level point of view here, there's no simple rule of thumb that's going to give you an answer to your performance problems, right? And no one size fits all, and that's why each particular case is unique and needs, like you said, some first principles analysis. So this initial talk I mentioned, I picked a provocative title, which is "What's Your Shape? Practical Steps to Understanding Your Virtual Workload," and we're going to focus on storage. So it's really important for us to kind of get used to this idea of workload shapes. Now, what is a workload shape? Now, different people define it differently, well, actually, most people don't talk about it using the term workload shapes, and I find it fascinating as a term because it really is this thing where you can think of your workload as having a form or a shape and start to kind of almost in your head visualize it that way. We'll see examples of this in a minute. So for us, the workload shapes technique for us is to use histograms. So I want to introduce this very deliberately. Histograms are much more informative than single numbers, and most of our tools today will give you a mean. So what is the average latency? And even if you have a tool that's giving you that at a 20-second granularity, it's still the average latency over that 20-second. So you can go move up the chain in your statistics mojo and talk about medians and comparisons of medians to means and look at distributions. You can look at the standard deviations from the mean and so on and so forth. The reality is that if you just plot a histogram of the latencies, let's say as an example, that you can see amazingly interesting behavior that can help you solve your problems, but would be obfuscated by looking at a simple average. So let's take a look at an example. I made up this example just so the numbers will work out, but seeing this sort of pattern is extremely common, and we'll see much more of that as we get down through the rest of the talk here. So what is a histogram? Well, a histogram is a very, very simple visualization, and the y-axis, let's talk about actually the x-axis first. So the x-axis, as in this example, is latency. It could be anything, but here it's a latency in microseconds of some I/O operation that's going on. So and the way to read this is to say, okay, well, there was never any recorded operation that had a latency of 1 or less, but there were 500 I/Os that had a latency of between 1 and 2. Okay, and that's the first bump that we see over here. Okay, so 500 is the frequency, a number of times that this data point was observed. So between 1 and 2, 500, give or take 500. And then 3 microseconds, between 2 and 3 microseconds, maybe about 1200 events were recorded, IOs were recorded that had this latency, and then so on and so forth. Now, if you look at this for a second, you realize that, oh, there's something really interesting going on. There's two different kind of clusters, two different types of latencies that are being observed here. And immediately you start to ask the question, well, why is it that there's this range? And usually that leads you to someplace good. But if you look at most tools, they will tell you that for this data set, and I did the math, the mean is 5.3, and that's what they'll say. Over the time period that this data was collected, the I/O latency was 5.3. When you scratch your head and you look at the two different ways of looking at this data, and you realize that there is not even a single I/O that ever completed in this workload that had a latency of 5.
And so if we were optimizing the system behind this for the mean latency of 5.3, we'd be completely missing the actual workload's latencies.
And I tell you that every single one of us who does not look at the more detailed distributions of latency today makes this mistake, because there's almost no way that the mean represents the actual distribution in the types of systems that we run. The mean may be fine for more natural systems, like for instance a classic thing in statistics is what is the size of the beaks of sparrows or something like that, right? And it's a very natural process, and usually there's actually a very simple distribution. It's not often not bimodal, and the mean actually represents something.
It's going to be that peak of the bell curve is what we expect the mean to represent.
That's right. But what if you don't have a bell curve? And the reality is, in most computer systems, there is no bell curve. There's just multiple different, clusters. They're bimodal, trimodal, multimodal behavior. What we're seeing here is bimodal, so two different modes here. And if you imagine for a minute, just want to explain why is it that computer systems are behaving like this, right? If this was I/O operations in this example, then on the left could be your cache hits. Now imagine that you have some DRAM cache in your plain old storage array. Even SCSI controllers have caches these days, right? Even most disks these days ship with some number of megabytes of read caches in that. So if you're getting some of your I/O hitting in that cache, you're going to see low latency, but the rest of your I/Os are going to see high latency. So very common to see bimodality and multimodality, and yet all of our tools today still give you the mean. It's remarkable.
Another way that you can get that is where you've got a database server that has sequential writes to its log volume and random reads and writes to its database volume, and they again will be bimodal in their behaviors, particularly since the database volume writes will tend to be really large, whereas the log volume writes tend to be fairly small.
Yeah, and we can get more nuance in that, even if you look at the writes in that case. Right, there's some of them that are going to cause flushes for the write buffers on your battery-backed storage array controllers. And those I/Os that are going to get stuck behind those flushes are going to take long, and you're going to get bimodality within the writes, or at least maybe multimodality. So it keeps getting nuanced, but the nice thing is that when you're dealing with a performance problem, that's what you're looking for. You're looking for that next level of detail so that you can do something about it, because if you keep seeing those means, you're missing out on the clues that are essential to solve your problem. And that's why I'm really passionate about looking underneath the surface a little bit in a way that tools today almost all commercial tools today are not able to do. Okay. So my kind of takeaway here is, why take one number when you can have a distribution just as easily? And we'll look at how easy it is to get these distributions later on. So we're going to look at histograms, and we're going to get really comfortable with using them in this talk. So what I'm going to present today is a workload shape gathering or histogram gathering technique that I implemented in the ESX kernel and has been shipping in ESX since version 3.0. It's called vSCSIStats. And it allows us to separate out each different type of workload into its own container and observe the trends. So for instance, if you have a virtual disk that's for instance storing the table space of a data space and of a database, and you have another virtual disk that's the index workload, and you have another one that's the logging disk for the database. Each one of them you can analyze separately and therefore do something about separately in using vSCSIStats. And so I want to talk a little bit about the technique, just to kind of hammer home how histograms work in this way. So let's just assume that this time around we're looking at a histogram of I/O request sizes. Okay. So an example of an I/O request size is 4 kilobytes. And it's a very common I/O operation size because of how NTFS and other file systems kind of have their minimum allocation size around 4 kilobytes. So seeing 4K I/Os is very, very common. So suppose that we have a workload that has currently the following shape. It has one I/O that has been recorded over this time period at 4K and maybe about 5 at 8K. Now suppose there's a new I/O that comes in that is also 4K. The technique, what it does is basically, you're going to have to watch this animation real close on the bottom left here, is that as that I/O comes in, the kernel will just add 1 to the count of 4K I/Os that it has seen. So, and this is extremely simple, very easy to calculate. The kernel can do this very efficiently without overhead. And what that allows is kind of I/O by I/O real-time tracking of I/Os. Every single I/O is accounted for, right? But not remembered in its entirety, only its range, which is really, really critical. Every other technique that you can use is not tracking every I/O, it's only tracking the averages. But this technique can actually track every I/O and be really at the real-time level. Okay, so now we know about how these histograms are calculated and why we want to calculate them. So now let's look at the types of data that we can capture in these distributions. So I'm just going to kind of put it up here. And to focus on the right-hand side, and we'll come back to the left-hand side. So if in terms of I/O size, there are 3 types of histograms that you can get. You can get all I/O sizes as a distribution, or you can focus on reads only, or focus on writes only. For seek distance, and this is quite remarkable, and we'll look at this in a lot more details as well. Seek distance is this measurement of how sequential or how random I/O is. And this goes back to around 2006 timeframe, when I literally on a given month I would get lots and lots of questions from customers, bugs filed that I would be involved in helping customers solve, and pretty much always it was storage. And one of the key things people would ask is, well, how do I know what workload I'm running? Is it sequential? Is it random? And I want to replicate that in a test lab and make sure that it's not ESX that's causing the problem, and so forth. And I realized that there was no tools out there to take a running workload and just be able to say, is this workload running sequential I/O or random I/O? So I invented this histogram called the seek distance histogram, and that helps us figure out random versus sequential. And I'll talk more about that in a minute with an example. And for that we have, again, all I/Os, reads only and writes only, really see the sequentiality, the randomness of workloads down to different I/O types. I'll skip over and show you the outstanding I/Os, and this is what we talked about before, also in terms of the parallel number of I/O requests that a workload can issue at a time. And we get that reads, writes, and all. Then we have I/O arrival times. What is the distance in time between when this workload issues subsequent I/Os? Is there a pattern there? And then finally, all of these different workload parameters result in the latency that the workload is actually seeing, that the application is seeing. And we track that both for reads, writes, and for all. So you can use this for simple analysis, like what is the overall read-write ratio? That's easy. But you can also kind of, just some examples of questions that you can answer. Are writes smaller or larger than reads in this workload? And that's really important if you're going to try to optimize your read-write cache on your storage array, for instance, right? Or size various block size parameters in various levels of devices. Are reads more sequential than writes? Very critical. You mentioned this one already. Which type of I/O is incurring more latency? And if you know that, if you can figure that out, then you can optimize for it. So I want to switch into some examples, Alistair. Let me know if there are certain things that I'm kind of not providing the right context for.
No problem. I'm not a quiet person when I've got questions.
Okay. So let's get into some examples. So here I have an Filebench OLTP workload, and I decided to run it on two different file systems. So the workload is identical, but the only difference is that the file system being used inside the virtual machine is a little different. Okay. Just to see what would happen. And we're going to use the next few slides to really exercise our histogram analysis muscles so that we can learn how to do this on our own. So on the top here, and in this slide, both of the histograms are the I/O length histograms, so the I/O size. Right? So you'll see I/O sizes of 512, 1020, so 1K, 2K, about 4K, about 8K, about 16K, and so on and so forth. And on the top row here, we have UFS, and the bottom we have ZFS, two different file systems in Solaris. So we'll look at the top first. So when you run this workload on UFS or any other typical file system, actually, what you would see is this workload is issuing a combination of 4K and 8K IOs. And in terms of IO count, over this time period, there's more than double the IOs of 4K compared to 8K. So, this is not an unexpected workload pattern for sizes for an OLTP online transaction processing workload. Now let's look at the same workload for ZFS. And what ZFS is doing is transforming all those 4K and 8K IOs into 128K IOs. And that, again, is quite remarkable that it does that. It does it so consistently. But it's able to do that because of the optimizations that are in that file system. And here is an example of something where even if you knew your workload, I'd say it was 4K, 8K, until you did the analysis of your particular environment, which includes all the perturbations of that application stream, including file systems and what the transformations that they're doing are, you wouldn't really be able to tune your system.
And this is again that rules of thumb don't work, because you'd characterize the application as issuing these relatively small IOs, and yet because of the file system, you may actually see that the storage array has to answer large IOs.
That's right. And again, you're absolutely right. If you go by the rules of thumb, if you go by kind of the published, from whichever vendor created the application is going to publish some best practices and so forth, unless you're really testing in your environment, you're going to miss it. Any kind of transformation that's happening, in this case by the file system, but it could be any other layer in the middle.
And this is also something that you're unlikely to see anywhere other than at the hypervisor layer or at the underlying array in a virtualized environment.
That's right. That's right. So this tool, and again, this was run using vSCSIStats, and is able to kind of say, look, given your workload, we're going to figure out the shape of that, right? Not just what it should be or could be or was in somebody else's environment when you read somebody's blog. What is it in my environment? And I'm going to use that to figure out my own problems. So the reason why I'm going through this example is just kind of look at a motivating example of why we need to do this, but also as a kind of exercise in learning how to read histograms. So now let's look at another example of this, and this is seek distance. So I promised that we would get used to this because it's one of the most interesting histograms that we can collect. Okay, so the seek distance is a measure of the sequentiality or randomness that is present in the I/O patterns that a workload is issuing. So if we focus on the top right here, the seek distance histogram, what we'll see is something kind of interesting. So we'll see the 0 in the middle in terms of distance and sectors, and then in the positive direction going towards the right from the 0, you'll see 2, 6, and so on. So kind of a log scale increase in the seek distance being plotted. And then if you start from 0 and go in the negative direction, you'll kind of see -2 and -4. So what is this? Well, each one of those buckets represents the distance in logical block number, so offsets on the disk, right, between two subsequent IOs. So if you were to see a lot of IOs in the 0 bucket, that means that it's a sequential workload because there is no distance between two subsequent IOs. Somebody issues an IO of block 0, then 1, then 2, and that gets subtracted out to 0 in each case because there's no distance between them. But if somebody is issuing block IO 0, and then the next block IO is to block number 1,000,000, and then coming back to some other random number, and then another random number, what you would expect is that the distance between those two IOs is going to be very large, randomly large, and so you would see peaks towards the right or towards the left. So in this particular case, if you look at UFS running the same OLTP workload as we saw in the previous slide, that this workload itself that's issued by the application is completely random. There's no activity around zero. And you'd expect this, again, because every data sheet that you ever look at for OLTP workloads would suggest that it's a random workload. It's transaction processing. So at any given point in time, you've got to go read a table from to represent some user transaction, and you don't know where it's going to be. It's going to be random. And so, of course, you would see all the frequency in this histogram being on the kind of the positive infinity, the negative infinity directions. And that's how you really read this histogram. You're looking for, look, is there a peak in the middle or is there peaks on the edges? In this case, the peaks on the edges. You expect that. But then again, we look at ZFS. Same workload, just a different file system, and you'll see right away that there's just a tremendous amount of sequentiality in that workload being generated through ZFS. And this is something that ZFS is doing. It's something funny that it's doing, transforming a random workload into a sequential workload because of how it works, and it can do this for writes in particular. It can convert random writes into sequential writes. But the reads it can't do anything about, right? And this is exactly the example that Alistair you were giving earlier, right? Which is you got a sequential write but a random read workload going on.
Yeah, and I kind of like the that top graph is the classic example of the wholly random workload, a sort of inverse bell curve where there's this big flat in the middle of there's just nothing. And yet, and that ZFS one, ZFS, where I come from, being English-oriented, that massive spike of sequentiality there is and the important thing to read about that sequentiality is that it is actually absolutely centered on zero. If it starts moving out to 6, 16, 64 as the seek distance, then it's no longer sequential. It's getting out into the more random space.
That's right. And so actually we'll look at an example of kind of a little bit of a hybrid behavior in a minute, Alistair, and we'll come back to this question that you're raising, which is at what point in time are you no longer sequential? And really it's quite disk dependent and workload dependent. I'm sorry, it's disk dependent, array dependent, caching algorithm dependent, and so forth. And that's why
the consequence of not being sequential.
Yeah, exactly. The consequence of not being sequential sometimes don't kick in until the distance between IOs, the seek distance, is megabytes or larger, which is why I kept that fine-grained distance, so 2, 4, 6, because otherwise I could have just kept, when I originally implemented this code many, many moons ago, I could have just kept, centered around 0 or not centered around 0.
Could have said, once you're out to 6 blocks offset on a 512 byte block, then you're away into the middle of nowhere. But
right.
I guess if we've got an underlying storage array like maybe an XIV, which works in 2 megabyte chunks, have to be read from the disks. So long as you're staying within that 2 meg chunk, you're still, as far as the spinning rust at the back is concerned, you're still sequential.
That's right. And a lot of disks can actually do optimizations where they don't have to do a seek if the next I/O is close enough. They just unsettle. This is remarkable in terms of the device physics. But if you're a few sectors, a few cylinders away, that normally you do a seek, modern drives, what they do is they just lift the head up a little bit, unsettle it, and then let the algorithm resettle it a couple of cylinders away. And that can be within megabytes of not needing a seek, just needing this unsettle. It's actually quite remarkable.
And then there's also that caching inside of the disk itself that may well be a read ahead and give me the next few sectors in case anyway.
Exactly. So I always kind of treat it as not very religiously sequential. And I say, look, if there's weight in the middle here, you're probably sequential. And if there's a weight in the ends, the negative and positive infinity, then it's probably random. And in this case, we see there's actually a combination. So again, when you see a combination like this, you know you're onto something. You might be able to solve your problem just because there's a pattern. That's what you're looking for, something that sticks out. So now let's look at seek distance in more detail, because again, it was kind of weird that in ZFS case in the previous slide that you had both this sequential and random. So now we get to take a nice, interesting look at this. Well, before we get to ZFS, let's stay for UFS at the top. What I've done here in this case is, whereas previously I was looking at all IOs, now I'm looking at the seek distance histogram for reads and writes separately. Okay, so now you see that for UFS, and as you would expect for an OLTP workload, that the reads and writes are both random. Now there's a slightly different pattern for how the randomness manifests itself between the two of them. Interesting stuff, for instance, that the randomness in the case of writes is always in the positive direction, and that happens for some workloads. It's a very interesting pattern. But for reads, it's very random, both positive and negative, and they kind of just mirror each other almost perfectly, which makes sense for reads in that case. Okay, so that when we split out reads and writes, we get to see for UFS a pattern that's still random. But when we do for ZFS, now we see that combination of random and sequential we saw in the previous slide can actually be explained away completely by the read versus write. Now we've proved our conjecture that Alistair had in the previous discussion, that the writes are the ones that are more or less sequential. So the majority of them are actually completely sequential, and then once in a while there's like a 1 meg or a 2 meg jump, so there's a little bit of a stride pattern, and then it's sequential for a while, and then there's a jump and then sequential for a while, and there's a jump and sequential. So that's really, really interesting of how ZFS is doing it. And if you look at the bottom right, you see the seek histogram for reads, and that's random. So really, the bottom two histograms are being combined in the all histogram from the previous slide, and now being able to split it out gave us a clue that we needed. So good to see that your theory is confirmed.
Yeah, I like to occasionally be shown to be right. Not too often, otherwise I'll get complacent.
Yeah, we're getting a lot of good practice looking at histograms and trying to make sense of them. And in this case, we looked at the seek distance histogram for this workload with quite a bit of detail.
And there's a fair bit here where you need to look at quite a lot of these histograms over time to get that sort of gut reaction feeling of what these spreads mean and which of the histograms you need to see. So there's a lot of value in even looking at a healthy workload and getting this information out to know what your workload looks like when it's working correctly.
That's right, that's right. So one of the things that I've been thinking about doing using the CloudPhysics tool set is actually kind of doing a lot of summarization of this, so that you have to resort to looking at histograms less often. Maybe we can just convert it into text, but I've not really spent a lot of effort on it. So if our viewers think that it's worthwhile for my team to go and invest in kind of automating a lot of this analysis, so you only have to look at the histograms when there's something that's kind of really extraordinary, but most of the time you just get plain English text. If that's something of interest, let us know. We'll go and build that for you guys.
I kind of feel that would be extremely useful if you could leverage experience of looking at lots of these histograms to be able to actually do the analysis, because to a certain extent there seems to be a straight correlation problem. If you see this particular shape on this histogram, it has this implication. But I suspect that that's only going to, it's not going to take away the need for the deeper analysis terribly much.
Right. Yeah, I have a hunch around that too. Would love to get some actual, customer feedback and user feedback, and love to get on the phone with some folks to just gather some requirements and try out some visualizations for an alternate way of looking at this data, which is more English and more straightforward and less, kind of visualization heavy. So yeah, I would encourage people to tweet me at virtual_Irfan, or hit me up at irfan@cloudphysics.com to just give me pointers on how you want to see the stuff, and like I said, we'll go build it.
The other thing I've found is we're just hitting an hour now, and so we probably want to find a nice logical breakpoint in the not terribly distant future, and we will definitely be carrying this conversation on in a couple of weeks' time.
Absolutely. So I'll quickly close up here. So far we've been looking at Filebench OLTP using a histograms technique. So I just wanted to kind of summarize what have we learned about Filebench, right? So it looks like the I/O from the application is primarily 4K, but 8K isn't uncommon, and this is the kind of analysis, summarization that you can do for your workloads and kind of try to make sense of them. It's very common also for the virtualization admin when he or she is dealing with a storage admin to take some of this data, summarize it, and then send it to the storage admin when you're dealing with a complicated problem. And let me tell you, there is nothing more pleasurable for a storage admin than to receive a workload report like this, to say, look, I'm having a problem with this workload, and by the way, here's what the workload is doing. Here's the shape of that workload. And I think we should start a hashtag on Twitter with photos of storage admins when you tell them this, because they just love it, right? It's so hard to get. It makes their life very easy and makes the virtualization of the server admin look really good. So that's the other reason to do it.
It's I think that's something that the sort of social impact of actually providing more information, trusting the teams that you're providing the information to give them deeper information. I think that kind of it ends up being as transformational for an organization as the technology stuff. So I really appreciate that kind of message of trusting the other teams and giving them more information that you have.
That's right. So just to finish off Filebench here, we notice that the access pattern is mostly random, but writes have this really weird forward-leaning pattern. Okay, so maybe we can do something about it, maybe we can't, but it's interesting to see it and to note it for future reference. And in particular, ZFS is able to transform random writes into sequential using aggressive I/O scheduling, copy and write techniques, log structured file system techniques, and stream a lot of sequential patterns on the disk. What I wanted to note was that when I did this analysis, now it's been a while since I did this, but I noted that the entire analysis that I did was done in a few minutes for this workload, which is really powerful because we're not dealing with you having to spend hours looking at spreadsheets to figure this out. You just have to look at the shape of the histograms, and all of a sudden everything else kind of just pops out. So what I want to do is, take maybe a minute or two, just kind of discuss high level with you, Alistair, or questions that might come up, but for, kind of lay out what we're going to talk about next time. So next time we'll pick up and look at a couple of other workloads. In particular, I'm looking forward to talking about Microsoft Exchange.
Gee, that's a common important workload, isn't it?
Yeah, and so I want to actually spend some time next time we meet to go into the details of this shape gathering technique and what it shows us for Microsoft Exchange, and then to kind of go from there and talk about what other things we can do with this and how to actually use this tool, and some things that people in the field have free utilities people have built on top of this tool to visualize it so that you get nice, pretty Excel spreadsheets like this and so forth. And that, I think, next time will be kind of a nice ending point for the workload shapes theme, and then in the following weeks we'll carry on with other performance topics.
Excellent. So our next session, the continuation of this storage workload shapes, is going to be on the 22nd of May. If you've just caught us because this content has come out in the main vBrownbag stream and you think you'd like to get up in the middle of the night, for those of you who are US based, we will be on 22nd of May New Zealand time, so that's pretty early in the morning. It's very early in the morning for you in San Francisco, isn't it, Irfan?
It is, but it's a pleasure.
Yeah, so thank you very much for proposing the session, bringing such really good content in, and we will be carrying on from the 22nd of May. So this has been the APAC edition of the vBrownbag podcast. Thank you very much, Irfan. Good to see my friends coming in live, and we'll see you all again in another couple of weeks.